So, hi students, welcome to another very exciting session of healthcare entrepreneurship. We are going to pick it up from where we left last time. So, let us get started. The next part is how do you do a design analysis. So, now we have this nice wonderful design for your product, but how do we know this product is not going to break or is going to be robust? Let us say you have designed this new implant for the dental purpose, and you do not know that with the daily mastectory loading, which is basically due to the chewing or any kind of trauma, this implant will break or not break. Or if you have an implant going inside the hip, basically, which is the classic hip implant, how do you know that this is able to bear the right load for a person who is weighing 110 kilograms or doing certain kind of activities like going by the stairs because his house is at the second floor without an elevator? So, how do you make sure this person, for this person, this implant is going to be correct and it's not going to get damaged over a span of, let's say, 5 to 10 years. So, you do something which is known as a design analysis, which is the next phase after having a design. Design analysis was historically planned for civil engineering folks, like, so it was typically done for buildings to look at whether a building is earthquake resistant. So, you could look at the effect of different kinds of loading when you have a building structure and see how the building would deform or fracture or fall down. Or if there is a particular bridge where so many vehicles or trucks are going to go over, is this perfectly supported? Will there be a resonance and the bridge will collapse or something or the other will happen? So, design analysis was typically kind of focused towards the civil engineering applications, but over time it has kind of come into the healthcare applications as well, and this is widely used in the form of that term which is known as finite element analysis. You may have heard of this term or may not have, but this is typically when we do a design analysis, this is known as finite element analysis. So, what we are trying to do through this design or finite element analysis is determine the effect of loads. Loads can be in forms of pressures or forces on physical structures and their components. So, we have this nice medical device which is going inside your body with a certain type of material with 5 or 7 parts. Any kind of implant has multiple parts. We want to look at which part will get damaged the earliest if the load bearing was like that in the human body, right? Our human body is constantly moving, and there are so many motions which are going along with loading and unloading, right? Which part is going to get damaged? Can we use a better material for it? Can we do a quick analysis without having to do a clinical trial on every material, which may not suffice? So, that is where a design analysis software becomes really important, right? Let us take T-word. So, how is this design analysis relevant in product development? So, some of the classic examples are, the first is example of a phone. I am not trying to indicate an iPhone here, but like phones in general, like smartphones, which typically what we have seen is it falls down every now and then, and every often, like I see every 1 in 3 person has a broken phone where the screen is either half cracked or this is completely shattered or whatnot, right? So, this was typically not the case if you think of 5 or 10 years back. Phones would take a while to really break, right? One of the things which I have observed recently is when there is a cutting corner within the business perspective where they are trying to make the screens and glasses for very cheap quality, then this usually happens. So, many of the Samsung phones I would earlier use, they are just doing fine, but one of the recent phones I bought for around 20 to 23,000 rupees. And the first time it fell like from a height of less than half a meter, and the screen completely got shattered. I had to completely get the screen replaced. So, that is a poor design, right? That's a poor design where something is not able to bear the load. This is one classic example. Think of another example in the mobile segment where we had this Nokia phone from back in the 90s. Many of us, if we were born around 90s or a little bit earlier, we would have seen this phone. This phone, there was lot of trolling and jokes around this phone that typically if you throw such a phone on a building, this building can get shattered. right? Or if this falls underneath the wheels of a truck, the truck will basically topple over, right? So these kind of things were jokes about it, but like long story short, what we did understand was this phone was extremely sturdy. This would just not break, right? Even if it fell in certain drains or something, it would still work fine. So this kind of a sturdy design is an outcome of very detailed design analysis. This doesn't happen like overnight. It's not like they have made the phone out of a rock, right? They have used phone very standard materials for the phone, but the design in which the different layers were modeled and how the robustness testing or the load based testings were conducted were done very right. So that is where this is a classic example with our regular phones these days versus this very simple phone which did not have a smart screen or any camera to say, was doing much more better in form of design. So we could think of in a very similar line about an implant which just very easily shatters because a particular company is trying to make money. There has been so many incidences of cases where particular startups or companies are trying to make more money by having designed implants which would go bad for sure within 2 to 3 years. So this is something which brings a very very bad name, and of course puts the healthcare takers, like, or which are the patients, at a huge risk of fatality and some injury or some kind of a really infection and whatnot, right? So whenever we are working at a startup or we are planning to look at the healthcare setting, we have to be placing utmost emphasis on the quality and have to be as much ethical as we can, like with the highest standards of regulation practices put in place, right? This is very very important. We cannot cut corners there. Even if a mobile phone goes bad, we can still live with that, but think about a hip implant which a person has gone through such surgical trauma which has failed within like 4 or 5 years. Replacing that by taking out that implant and putting it back, how much of a surgical mess that would be, and so much of trauma and pain. So that is something we should be, as an entrepreneur, thinking about. We should have empathy for the end users what we are trying to serve. It's not always about the money, like at the end of the day we have to think about giving a very high quality product also, because if we do have that, then you will be known as a brand. So for example, if Johnson and Johnson and some other companies are known as a brand for certain medical products, they are known as a brand for a reason. Or Abbott, or let's say certain companies which are building this diagnostic devices, if they are known as a brand, they are known there for a reason. It's not only the kind of sleek looking things which they have, the quality is very good. It is something which the doctors like to use, right? So this is another example here. This is of the very classic Fiat Padmini, and I thought like this would be just a nice example to take besides the lot of healthcare chats which we are having. So this Fiat Padmini is another example of a very nice design. Back in the day, this is a car which many jokes and trolls have gone around, and of basically around the fact that this car is so heavy and so sturdy that even trucks and buses would be very careful while coming in its way, right? Like if you hit it with a bus, probably the bus will get damaged. That was the joke going around. But the idea here is very similar to the Nokia phone. This was a very nice design, right, which had such a consistent kind of materials and set of design parameters which were used to build this, that this would not get damaged very easily even if you have an accident. You look at majority of the cars these days, you go with a 20 kilometers per hour, you hit a small curve, it will be a huge damage on your bumper, right? So that's the kind of design element which has changed over time due to, of course, mass manufacturing. There is a lot of requirement, there is cost cutting, there's cutting corners in terms of design. So those things are fine, but from a medical standpoint, you cannot afford any kind of design issues like in your product, like to go ahead with. Your startup can totally fail if implant is all that your startup makes, and it gets one bad review when somebody has probably died or somebody has gone into some kind of a surgical trauma due to your implant. A lot of us have seen documentaries and series and so many things around the pharmaceutical industry and several other drugs which are clinically trialed, and we have seen some myths about, like, when a particular drug was used for repurposing and this was wrongly given to a certain population. So that is where it had a very adverse effects and somebody died, and basically that entire company had several lawsuits against them, and this entire thing can go down the drain, right, basically. So as a startup owner or an entrepreneur, we have to be very careful about the quality of the design, and in order to do that, we have to do a design analysis. Okay, so let's talk about some of the examples in product development where we have used a design analysis. So these are some pictures you're looking from a design analysis software standpoint. So the color maps are basically kind of indicating the different levels of stresses or stress. As we can all know, stress is something which can lead to a possible breakdown or fracture. Very high amount of stress on any kind of model or mechanical model is not desirable. So if I have a certain kind of shoe or insole I have designed, and beyond a certain load that shoe can get damaged, so that's a high stress basically, right. So let's look at the top figure on the left. We are looking at the classic hip implant, and we are looking at a finite element modeling or a computational modeling of the same within the femur, and this has been tested against different loads, and there are different designs to it, very subtle design elements. If you look at it, the first one has a much more wider stem or the bottom for the implant, and the second one has kind of a narrow stem, right. So these are different designs out there in the market, everything having different rationale why they're like that. But the idea here is to understand that which one here is going to add to more stress at the interface of the implant and the bone, as well as to the bone, as well as to the implant itself. So these are the three components: the implant, the bone, and the interface. So if you have a lot of interfacial micro motions, it's typically known as motion or relative motion. Little bit of micro motion is okay in this aspect, but too much of micro motion basically means your implant may detach from your bone, right. That is not a good thing to look at. Or if you have a area of high stress zone indicated by the red color, very flashy red color, followed or surrounded by an area of very low stress zone, then this particular area of high stress zone is susceptible or vulnerable to fractures. Okay. So whenever the stress value of a particular region goes beyond the value of the material strength, which is usually known as the ultimate tensile strength of a material. Now, this is one of the mechanical terms many of you may be aware of. So once the value shoots over that point, then in that part there will be a fracture or a breakage. Whenever there is a slight fracture, it starts to propagate, and then it could lead to the complete failure of the hip implant, or could lead to the failure in certain aspects which can cause several detrimental things. So it might be a nice idea to test all the new designs of hip implants through a finite element or a computational software, design analysis software, before these implants are actually going through a clinical trial or other set of trials, right. So that's why design analysis here is important. Let's look at the second example. Here you are looking at an ergonomic chair. Ergonomic chairs are typically designed for folks like us who are in front of the computer for more than, let's say, 6 or 8 hours, because we are typically sitting in an office environment, or we are working in an IT field, or it could be professors like us who are just sitting in front of computers for such a long time. So there is a high chance that if this chair doesn't have the right angles or the right comfort which is provided to me while I am sitting or relaxing or weight shifting my arms and doing other activities, then it may cause some pains on my body in certain locations, especially the neck and back pain, and there could be possible elements of fracture or rupture within the chair itself. So maybe this particular chair is not designed for a person who has 110 kgs of weight. It could be beneficial for a person who has maybe 50 or 60 kilograms of weight, right. So how do you design an ergonomic chair? Ergonomics basically deals with the area of comfort. So how do you make a comfortable chair? This is another area where a new design can have a design analysis, where the red zones are usually the high stressed and blue zones are low stressed, you could well imagine majority of a load is underneath our hip, so that is the high stress zone. If the stress red doesn't always mean it is bad, it just means an area or the distribution. What is the value of that red is very important. If that value of that red comes as, let's say, 21 megapascal or some gigapascal or whatnot, and that value exceeds the value of the material which this chair is built up of, then this chair will break or have some fracture. So that is the understanding. Red or blue always doesn't mean the bad or good, it basically means it's a distribution. On top of that, we have to look at the value. Okay, let's look further. So the third one is a mobile phone, and basically it's doing a stress analysis on the mobile phone. Again, this is the distribution. The fourth example is of a solar panel, quite different from the healthcare examples, where they are trying to look at the solar panel weights, and it is going to be hung around well on this particular roof. The fifth example is a little bit towards trauma and injury. This is for crash testing of an automotive vehicle. So if you are looking at any particular vehicle, like let's say from Hyundai or Tata Motors, or it could be Maruti, they have to typically go through a lot of crash testing activities when they launch a new vehicle, to look at whether their airbags are getting deployed properly, whether there is a huge jerk to the passengers which can cause a traumatic head injury or fracture in certain zones. So they have to typically spend a good amount of cost and time breaking a few vehicles to look at the extent of the damage analysis. If something is moving at 100 kilometers an hour versus if you get a hit at 30 kilometers an hour or get a side hit from a different car, how does it really affect the passengers? Because at the end of the day, it's the passengers, right, that what is important. And of course the car is also important, it should not get damaged too much. So typically you can do through a design analysis software these kind of car damage analysis. These are fairly complex analysis because you have so many parts of the car, of the human dummy and whatnot, and these analyses are usually fairly accurate, and you can within a few minutes have this car simulated at 100 kilometers per hour, 120 kilometers per hour, 60 kilometers per hour, every possible scenarios you can look at, and you can get very deep data or deep insight into all the components, how they are getting damaged or how they are getting affected due to this sudden head on collision or a side collision. Think about doing the same for your implants. If you have an implant which is devised for this specific rehabilitated population who are going for the Paralympics and so many other aspects, if you are designing something for them, you want to do this kind of design analysis to make sure they are the most efficient while they are looking at their athletic activities, right. So these kind of similar platforms, design analysis, can be carried on to so many different applications. That is something to be looked forward to. The sixth example here is of a mesh. Basically this is of a hernial mesh. Hernia is basically a disease which occurs typically at your around your abdomen or belly region, where an organ basically protrudes out of your soft tissue region. Extremely painful. Typically how this is corrected is you have a hernial mesh typically made up of polypropylene kind of material, and this mesh creates a hammock, and you stitch this mesh along the side of it and put the organ back where it should be, and then this mesh doesn't allow the organ to protrude back in, right. That's the idea of hernia repair. So typically what this is doing is the sixth example, it is trying to look at the different strands and microstructure of these hernial meshes, a lot of which are known to fail. If you look up hernial meshes, you will see a lot of lawsuits across the globe. They fail in the form of like not able to contain the hernia, or there are twists, there are infections, and so many other modalities in which they fail. So this is basically looking at the structural integrity of a mesh if it is subjected to different biaxial loads. Biaxial loads basically means a mesh is basically stretched along the two directions, and within these two directions you are trying to see if the loading is too much and all of a sudden there is a jerk or an impact while a person is running or trying to climb a step. Will this affect this hernial mesh? So these kind of testing has become more and more important as an integration of engineering and healthcare. So, majority of the mesh manufacturers like Johnson and Johnson, there are companies like Boston Scientific and so many other companies are producing this meshes. So, these companies are typically testing it in a dry testing mode and do not have this design knowledge where they can test it in different scenarios when they are interacting with the tissue around it or the stitches around it, and see how it would affect the stitches versus the tissue versus the mesh. So, this kind of information is only available when we integrate our minds of engineering and design analysis along with these kind of clinical aspects. So, my research group earlier had been working on this area in which we looked at this particular hernial meshes and this its stretchability and interaction with the stitched soft tissue around it, and we use different synthetic skin and other modalities to check on that. So, design analysis software gives you an opportunity to do this testing at different loadings and scenarios very quickly. So, just an overview of what finite element modeling is, typically what we are talking about. So, finite element modeling goes by the process of discretization of a model. So, this is the keyword, discretization. So, what typically does happens is we have talked about design so far, right, where either we have created a design based on our initial software based modeling or taking some dimensions from 2D designs and converting it into 3D designs, or we have talked about DICOM based images or 3D scanning of a outer periphery of the human body to get a design or model being done, right. So, once we have this model, the next thing is we call this as a geometrical model. We break this entire model down into small pieces, which is known as this finite elements. Okay. So, we discretize or break this model down into the small pieces, which helps us solve a very complex mathematical equation. So, typically what happens if you have look at strength of materials and these kind of topics like finite element analysis from a very mechanics of material standpoint, then basically there are so many equations which describes the kind of a truss kind of element. If a loading is applied on one part of this table, what is happening on the other part of the table is usually obtained through several mathematical equations, or a beam or a simple supported object. So, that kind of mathematics is now applied to these complex systems by breaking this down into the small elements within which the small section mathematics happens, and overall this math is propagated across the entire set of elements. And finally, what you see is if I apply a load at one point in this foot model, which I have got from here, you can understand the stress distribution or pressure distribution at all different aspects of this foot model in any point, any direction, and all the surfaces. So, this is what the beauty of the finite element model is. So, here typically what we had done is we did not have the scanning software back in the day. We had specifically taken a person to come with their like foot ailment, and basically we had put a cardboard with 3 rulers to take different points of coordinates on a sock which they are wearing. So, we had taken around 1200 points ish, like of 1, 2, 0, 3, 2, 4 or 5, 6, 7, these kind of coordinates, spatial coordinates we took, and finally we had created this geometry very similar to scanning. So, this geometry was created using something which is known as a bottoms up approach, where we go from points to lines to areas to volumes. So, finally, when we get to this volume, we discretize using a finite element software, and we apply the necessary amount of load on the red section, which is basically if I am a person weighing 60 kilograms, I would apply typically like a 30 kilograms on this particular red section, right. So, that 30 kilograms then finally is processed through this software, this finite element software. Typically, one of the softwares is ANSYS, which I use. You are welcome to use several other softwares like HyperMesh. There is a modality of finite element analysis within the SolidWorks framework itself, and there are so many other softwares which are there in the market, right, COMSOL, Multiphysics and so forth. So, finally, we run a simulation with this and we are able to see the final diagram which we were looking at in the previous slides, which basically shows us the distribution of the stresses all across the foot while we are placing a simple load of the foot as if we are standing. right. So, this is the distribution with the highest load being concentrated at the heel region, which is totally correct, and with some more loads concentrated at the metatarsal or the toe region. Rest of the foot is kind of around the arch, it is low amount of loading, right. So, this is normal loading, the values are typically fairly low. We are looking at megapascals. So, Pascal is a unit of pressure or stress. So, it is given by force upon unit area, right. So, pascals is given by 1 Newton per meter square. So, when we convert that meter square up and above, it becomes megapascals kind of, when we are looking at units of millimeters and newtons. So, typically in an ANSYS environment we work with millimeters and newtons. So, when we convert that, we get megapascals. Most of this finite element modeling softwares do not have dimensions. So, we typically consider an initial set of dimensions, like I have said, millimeters and newtons. So, all the results would scale accordingly. So, whenever we get results about pressure and stresses, they would be in megapascals, right. So, what are the typical steps of a finite element model? You would see typically you have a constraint. So, here we are looking at a foot model with an insole. So, you would want to fix at least one of the models and have an interaction between the other models, because otherwise the computer just thinks that this model is floating in free air, it does not create a constraint. So, you need some constraints, fixed constraints, then you have some loads, right. So, this fixed constraints and loads together, and then you have a contacting or a contact pair kind of condition within the insole and the foot, because the computer does not really understand whether this insole and the foot model are related, right. So, this insole model we had created by hand within a SolidWorks software underneath the foot model, basically by taking its dimensions. So, these two models were attached. We have applied a bottom constraint to the insole by considering it to be the ground. So, you cannot move your foot any further or your insole any further. Then we have applied a load of close to 30 kilograms in the terms of pressures, and then we have run an analysis. So, most of the software like ANSYS, there is a student version which is free for use. You can download it from the ANSYS platform. I will showcase from where you can download it, and you are welcome to learn about it through some tutorials which are available on YouTube and so many other places. It requires some kind of learning curve, you know, like probably a few weeks of sitting to get a hands on like into these kind of softwares. But typically once you get acquainted, like you can test any kind of physical products, like for their robustness and different forms of testing. Another thing to notice that there are two types of softwares typically there. One is a static software. Most of the ANSYS works with a static kind of framework where you cannot apply dynamic or impact loadings. Then there is another set of these software extensions like LS Dyna, and there are you know, several other softwares which offer a dynamic modality. There are softwares which allow you to look at the interaction of a fluid with a, if you have fluids within an artery model or something, fluid with a structure, that is CFD, which is computational fluid dynamics. Quite extensions of this finite element method in certain forms and shapes. So, these kind of softwares you can use to easily analyze the interactions with different objects, you know, how this particular implant is going to interact with the bone around it, how is this dental implant going to stay in its right place, whether this is going to get damaged after 200 cycles or not. So, these kind of dynamic softwares you can look at, right. So, these are the key steps. This is one example where this is a live example. I was talking about one sole. So, what we typically did was we were focused at the diabetic ulceration. So, we were looking at patients who have some possibilities of developing ulcers on their foot because they have a really high degree of diabetes, and we created some ulcer shapes and some propagated shapes like which keeps on going bigger, and we wanted to basically test whether there we can select an insole material which will really offload the amount of stress which is going on to the ulcers, because that is very important. If the ulcers are getting stressed around the walls of the ulcer, they have a high chance of propagation and further going for a, you know, typical further ulceration and gangrene and needing for an amputation. So, this can really aggravate itself without much healing. So, we wanted to basically look at how can we reduce the amount of stress which is going at the ulcers. So, we have published quite a few papers on this, looking at all possible locations of the ulcers and how the weight shifting can have an effect, how the insoles can have an effect. So with this we came out from this design analysis with certain insole forms which had certain materials which we tested. You can see here in the plot here where we have looked at no ulcers with a custom insole, circular ulcers, irregular ulcers, circular ulcers with an ulcer isolation design. This is one of the patented designs which we had, where we wanted to isolate or cut out a little bit of region around the ulcer. This could be a custom cutout for somebody's ulcer, and basically through this cutout there is a complete offloading or isolation of this place. So there is no more loading, right? And what you are looking at in the x-axis are the different forms of materials. So we had taken quite a few materials from which are available in the industry for insole manufacturing, and few new materials like the synthetic skin materials we had been talking about in the previous classes on the customer discovery, right? So based on all these materials, we found out that basically the ulcer isolation design was working very well for offloading. Fairly intuitive, but we could test it very easily with different material combinations. Along with that, we found the material 10 which was the most material 10 is not the most effective, it's probably the least effective in this case. So the material 1 through 5 or 1 through 5 specifically were leading to the minimum stresses which were generated near about to the ulcers. So these 1 through 5 materials were something which we found as a good fit for our particular insoles, and then we finally 3D printed those insoles through different manufacturing processes, and we had this as a product. So something to look into is what we started designing was the foot. What we analyzed was some models of the insoles, and what we further built was the insole, right? So our product was not exactly the same as what we designed, but we did design the insole which was part of the design analysis. So but the initial design was on the foot. So some of the key steps of this FEM analysis includes understanding the stress and strain distributions, the effect of material properties on the results, identifying defect specific stresses or strains. So are there certain locations where stresses are very high, which can be pinpointed. Effect of interventions on stresses and strains. So this analysis gives us an insight that we can use implants, we can use wearable devices and look at what is the effect of their loading on a particular person or generic population. Another very key example is, think about an astronaut who is wearing a lot of wearable sensors which gives feedback on his vitals and whether he is doing okay. If his health goes bad during his space travel, he can be kind of guided from the space station basically that what are the key modalities or differences he needs to make like in their day-to-day activities so that he recovers better, right? So these kind of sensors he's loaded with his space suit. So if that can be tested, like his amount of wearing and other loads which is has put on his body can be reduced if these kind of sensors or sensor assemblies can be design tested. This is one example. The other example is again around the astronauts. So typically when the astronauts come back after a lot of anti-gravity kind of training and exposure, typically they develop arthritis to some extent, a certain extent. So they have a lot of reduction in their bone density. So for some, they are not able to stand or walk properly for a few days. They have to be trained back in the Earth's environment. So few of these testing modalities can be conducted in these kind of design softwares to look at what are the new kind of exoskeletons or shoes or devices which can be built so that they do not have to spend too much of time adapting back to the Earth's environment, which is much more with the gravity, right? So there could be so many applications going from the surgical bedside, from the clinic to all the way up to the astronauts where medical devices, wearables are used, and you can use design analysis. So with that, I would just like you to show see this particular window, which is basically a standard window for this ANSYS design software, and this is the graphic user interface. What you are looking at is one of these analysis which has certain parameters which has thrown out. These are basically the numbers of the results. The color map is shown in terms of without any dimensions. You are looking at the stresses and displacements here. So in one screen you can either see the stress, strain or displacements, right? and typically you have a lot of options here to place different loads, constraints and whatnot, and you can work on this device. You can download ANSYS student version free of cost from the ANSYS website, right? So with that, I would like to conclude. These are some of the design solutions or tools which we use for designing and building physical prototypes and physical forms of the products, as well as for testing those products to make sure they are robust and they can run the test of time.